We just saw a proof of the midline theorem. And the midline theorem, what it a priori says, and I'm going to try and trace over your triangle that you drew here, is we start with a triangle ABC. By the way, here's a comment I'm going to make. Anytime you draw a triangle in a proof, try not to draw it equilateral looking, because sometimes an equilateral triangle, things look to be true in your diagram that might not necessarily be true. I'm going to let that ride on this one, because we have bigger fish to fry, but A, B, C. And so what the midline theorem says is that if we take the midpoints of two sides, so let's call those midpoints P and Q, as was done in the proof, and by definition what midpoint means is that the segments on either side are congruent, so P bisects AB and Q bisects AC. Now you can see why having equilateral makes this a little strange, because it would look like all four of these are congruent, when in fact it's just two pairs. So if we take those two midpoints and we connect those two midpoints with a segment, PQ is something we call then the midline of this triangle. Then what the claim is that, first of all, PQ is parallel to BC. So the first thing that we need to substantiate is why we can draw these little parallel marks in the triangle. And then the second thing that we need to justify is this even more incredible statement about the lengths of those two segments, namely that PQ is half the length of BC. So not only do we know that they're parallel by the end of this proof, but we also know how their lengths compare one to another. So when we cut AB and AC in half and connect those two midpoints, that connecting segment has half the length of the third side of the triangle. So that's the statement of the midline theorem. So I kind of want to talk through the various elements of the proof that we see on the board here and try to highlight their function a little bit. So let me ask you all of this. What was the point of this first phase of the proof? What were we doing here?
We were proving that, I'm sorry, I shouldn't
Yeah,
even
go ahead.
answer this question. We were proving that P and Q are midpoints of AB and
We were
AC.
proving that P and Q were midpoints of AB and AC. So here's my suggestion. The statement we had of the midline theorem begins with, if P and Q are the respective midpoints of A and B. So actually that's not something we had to prove here. We didn't have to include that part in the proof. That was given to us in the hypothesis, in the antecedent, in the theorem itself, right? So we know P and Q exist because the theorem says, let P and Q be the midpoints. So that's what was happening there. So we have P and Q, they're the midpoints of the sides AB and AC respectively. Then comes a creative element in this proof, which is right here. So the way that this proof proceeded is that we took the midline PQ and we extended it. We made it longer. And we did it in such a way that when we made it longer, we did so to a new point T. And what was important about that point? How do we define what T was?
So that PQ is equal to QT?
Yeah, this was the key element right there. That we extended it so that Q itself was a new midpoint. This is a promising strategy in this proof because it now gives us a new pair of congruent sides to work with, PQ, congruent segments, PQ and QT. And so our job, if we can do it, what we would like to do is to show that when I connect T to C and I make this parallelogram, PTCB, if I can show that is a parallelogram, sorry, I'm getting ahead of myself. If I can show that that's a parallelogram, then on the one hand, because it's a parallelogram, we would know that PT is equal to BC, because parallelograms, opposite sides, are congruent, right? So that's one thing we'd know, but on the other hand, by construction of the point T, we already know that PQ and QT are congruent segments, because Q is the midpoint of PT. And therefore, if those two congruent segments added together are the same as BC, then one of them by itself is going to be half of BC in length, which is what we were trying to prove. Right? So all we need to do is to show why PTCB is a parallelogram, and then we've got it. And that's the content of what we saw at the end of the proof down here. As long as we can show PTCB is a parallelogram, then that means that PT is congruent and parallel to BC, and that parallel is the first element that we needed for our proof, right? It's the statement in orange up here at the top. PT is parallel to BC. And that's going to show us why that's true. And then chasing the rest of the logic through, showing that PT is half the length of BC, that justifies why this statement is true up here at the top. But the hard part about this proof was that we didn't know off the bat that PTCB was a parallelogram, so we had to take this digression over to the left side of the board. And we had to introduce a new quadrilateral. That new quadrilateral was, I need a new color. How about red? No, not red. I've already used red. How about this dusky purple? APCT. If we can show that that quadrilateral is a parallelogram, then we use that information to show that the other quadrilateral is a parallelogram, and then we were home. And the key ingredient is, because of the construction of the point Q and T, we automatically, in my purple quadrilateral here, have bisecting diagonals. And as soon as we have bisecting diagonals, we have this result, 2.3.3, that tells us that ATCP is a parallelogram. Great. So because it's a parallelogram, it has opposite sets of congruent sides, which lets me put a red congruency hash on CT. But now I have red congruency hashes on 3 different segments, AP, TC, and PB. And what's more, because that's a parallelogram, its opposite sides are also parallel to one another. I need a double parallel hash right there. And so what I end up getting, let me put one more double parallel hash right there, is I have 3 congruent parallel segments, one pair of which are PB and TC. And according to 2.3.5, having one pair of opposite congruent parallel segments is enough to guarantee for us what we needed to guarantee, that PTCB was a parallelogram. So there's a lot that goes into this proof, and the midline theorem is really the engine of everything else that we end up proving in 2.4 as we work our way towards the proof that the medians of a triangle are concurrent.